Hey guys, welcome back. We are still doing chapter 1 and 2 review, and now we're going to talk about the chapter 2. Okay, so this is a lot of data. I probably need a calculator. I don't think I brought one in. Okay, I'll use my phone. So each box plot summarizes 24 students, and a box plot is a 5-number summary. So on a recent 2 different classes, the box plot drawn uses a common numerical scale. Okay, which must be true. So when we look at this, we see that, and if you looked at the answer in the back of the book, it says the lower 25% of class B, so that's this part, are much more spread out than the lower 25% of class A. And that is definitely true. So you would have taken the time to read through all of those, but E is absolutely positively true. So again, I remind you to get all of your points, make sure you write this out in a sentence in your own words, or make a sketch like what I've done here, or highlight these 2 little legs, something like that to show that you're not just highlighting and writing out a letter. Okay. Question 2 is for question 2 and 3. The height of 250 men and 200 women were measured. The distribution of these men's height had a mean of 68 and a standard deviation of 3. The women's distribution had a mean of 65 and a standard deviation of 2.5. Both distributions were approximately normal. Okay. Now, which must be true? So when we look here, we know this 95, 68, 95, 99.7 rule applies. That's having to do with 1 standard deviation, 2 standard deviations, and 3 standard deviations from the mean. So the percentage of women shorter than 6.25 is smaller than the percentage that's shorter than 65. So I've got to kind of write out one of these. So that's 1 standard deviation less, so that's 65. And what's 1 standard deviation less? That's 62.5. So essentially they're saying one is smaller than the other, and the answer is no, they should be the same because they're both 1 standard deviation under the mean. There are a higher percentage of women between the heights of 62.5, so that's 1 standard deviation below the mean, and 67.5, that's 1 standard deviation above the mean. So essentially that's saying between -1 standard deviation and positive one standard deviation. And for men, this is saying the same thing because 68 plus 3 is 71. So once again, these should not be different. There's not a higher percentage. There's exactly the same percentage. In fact, there's exactly 68% if it is normal distribution in both categories. So it is the same. So that's going to be false. C, more than half the men are taller than 68. No, not more than half. Exactly half are taller and exactly half are shorter. So that one's no good. D, approximately 95%. Well, 95% is 2 standard deviations away. And of women are between 60 and 70. So what's 2 standard deviations? So that's 5. Yeah, that's 2 standard deviations, 60 and 70. And 95 are between 62. Yep, 62 and 74. So my answer is yes, true. Which of the following is not a correct statement? Men's heights have more variation than women. Okay, that doesn't sound right, does it? But let's keep reading. Men's heights distribution is more skewed than women. Well, based on the data we've given. Oh, well, based on the data we're given, remember it said, this said for both problems. If I look at this data, I say to myself, wait a minute, they do have slightly more variation because standard deviation is a measure of variability. So I thought, just because you're a guy doesn't mean your height is more variable, but based on this data, that is true. Nice, okay. Question number 4, a teacher found the mean number of hours her 12 students spent studying for the AP exam was 67. So they added up all these hours that they studied and they divided it by 12 and they got the number 6.7. Okay. A new student from across town is transferred in and reported studying 11 hours a week. What is our new mean? Okay, so we did a problem similar to this, but let's go ahead and calculate this. So I could pretend that all 12 students have exactly the same amount. So it would be the same as all 12 studying for 6.7 hours. So let's multiply that. So I get 80.4. And so I can take that 80.4 and then add it to this new 11. And I want to divide it by 13 because now I have 13 students. And that should give me the average. All right, so if I add that to 11 and divide by 13, I get 7.03. And did I get an answer like that? Yeah, B. Nice work. A small department at a university is seeking faculty raises. The university claims to pay the faculty in the department is comparable to other departments, but the department claims they're paid less. The university and the department both base their statements on a mere typical salary. Using data included salary information for all faculty at the university. Administrative salaries tend to be much higher than when we compare them to faculty. Which of the following is the best explanation of their differing interpretations of the same data? So you have these answers here. Let's see if we can make sense of the answer we were provided. So we were told the university compared the median salary to the median salary while the department used the mean. Interesting. So a typical person could have been paid less, but the mean would have been more variable. So that kind of points out the difference there. Interesting question. All right, question number 6. 2 data sets have different variances. So we had that example a minute ago where the men and the women had different variances, or they had different standard deviations. A's constant of K units is added to all the numbers in both data sets. Okay, so if we think about this, remember, let's think it was our heights. So the tallest person is 80 inches and the shortest person is 60 inches, right? The range is 80 minus 60, or these people's heights range by 20, right? And that's one measure of variance. If a constant K was added to all of these numbers, then you'd still have 80 plus K minus 60 plus K, and you end up just getting 20. So we know that both of the variances will stay the same. When we add, so the rule is when we add a constant, standard deviation and measures of variability don't change. But they do change when we multiply. All right, number 7. Which meters are considered not resistance, meaning very movable? Well, we know that the mean is movable, the standard deviation, and the variance are all movable. So these are highly movable. All right, hold on a second. I got to turn on the light. It's getting too dark in. We know the median is less variable. So we're definitely going to not pick these. And we know that the median is less variable. So that's kind of how I've eliminated. The IQR is a measure of variability. So I could see why we might pick A and E, but we only use the interquartile range if we're using the median. You see what I'm saying there? So that's why E is kind of a better fit. Okay. 8, every observation in the data set is multiplied by a constant. Multiplied by a constant K. So we know that that's going to change the mean and the standard deviation, both by a factor of K. That is what our notes say, and that's exactly what B is. So to get your points, don't write B, write this sentence out, because that is the sentence in our notes that we need. And write this sentence, this part of the sentence out. So when I multiply by a constant, the mean and the standard deviation will both change by a factor. All right, let's look at these box plots for the next 2 questions. Which box plot summarizes the data is skewed left? So let's look here. Looks like, oh boy. I'm definitely thinking B looks skewed left, right? This one looks skewed right. This one looks skewed left. This one looks basically symmetrical. This one's got these outliers, so it's gonna mess up its skewness. So I'm gonna pick B. And again, make like a quick sketch. Okay. Now let's see. Question number 10, which box plot corresponds to the following histogram? Okay, so we got an outlier out here, so we definitely want to pick, narrow it down to D or E. And let's look for what's other consistencies or inconsistencies can we look. In our 5-member summary, right? This looks relatively symmetrical and one outlier. So let's take a look back at our question. I'm trying to narrow it down to D and E. And it looks like this is, let's see. It's kind of a, I think I like E better. Let's see. Yeah, because look, this here is further to the right as well. So if I look at this middle line is further to the right as well. So yeah, I'm going to pick E. All right, which of the following statements are true? Variance is smaller when extreme outliers are present. No. Yeah, that's absolutely false. Outliers make the variance go up. Look at the fact that this outlier is here. That means the spread outedness of the data is more spread out with that there. So we can't pick one. And we narrowed it down to B and D. The interquartile range, IQR, describes the spread of the middle 50% of the data. This is the definition of interquartile range. So I like 2. Now I have to decide on 3. The standard deviation gives a relative position of a value from the mean. It's not a relative position. No. The standard deviation tells you the average amount that any one value is from the mean. So that would be false. So I'm going to pick 11. We will pick B. All right, number 12, a group of 15 workers are on an assembly line. They have a mean of 15.2. So if you don't know their individual numbers, we know that they must finish in a total time if we multiplied them. Then it says a second group of 21 workers has a mean completion time of 16.8. So we could figure out their total time if we multiplied them. And we can't figure out the individual times, but we know their total time should be how many there are times their average. What is the mean time for the combined group of workers? Okay, now we got to be careful here. We can't just average these two numbers together. That's not going to work. I can't just take, so it's kind of like a weighted average. I got to find my total time here, right? So 15 times 52.2. So 228, 21 times 16.8, 352. Pencil's starting to wear out here, sorry. I'm going to add that up to figure out my total time. So for a total of 36 people went for a total time of that. So I can divide that total by 36 and I get 16.13 repeating. So that gives me D, 16.13 repeating. The distribution of heights of 150 students is approximately normal. Okay. With a mean of 65 and a standard deviation of 2.5. Which of the following intervals would contain approximately 102 student heights? So what proportion is 102 out of 150 students? Let's figure that out. 102 divided by 150 is 68. Interesting. Well, the 68, 95, 99.7 rule states that they're within one standard deviation. So if I take 65 minus 2.5, I get 62.5. And if I take 65 and add 2.5, I get 67.5. And that would be my answer if that's one of my choices, that 68% of my data is between 62.5 and 67.5. And that is one of my choices. Nice. Okay. 14 says, a 2-year study of high school students in the 80s measured the time to complete 1 mile. The mean boys was 460 with a standard deviation of 55. And the mean girls was 591 with a standard deviation of 70. Both distributions are normal. Darnell ran the mile in 394. So I'm going to take, he's fast. He's much faster than the average male. Christina ran the mile in 500 seconds. She's fast. She's much faster than the average girl. Assuming the distributions of run times have not changed, which student actually performed better or which one ran faster? So we're essentially looking for which of the person is further away from the mean. So in this instance, we want the person with the highest z-score, negative z-score, like a really low z-score. I guess that would be the lowest z-score. Okay, so the z-score formula is A minus P over S. The actual, so his actual is 394, right? And we'd predict for him to run the average time over the standard deviation of 55. And then when we look at, this is Darnell. So then when we look at Christine using the same formula, her actual time is 500. And we expect her or predict her to run 591. And standard deviation is 70. So crunching these numbers quickly in the calculator, I get negative 1 point. And it looks like Darnell might be 394 minus 460 is negative 66 over 55. Yeah. So it looked like for a moment Darnell was faster, but for a girl, Christina was actually faster because she's further away from the mean, which means much faster than the average. So let's find that answer. We get B. Christina is the one that performs better with a z-score of negative because being further to the left than Darnell's score. And the lower your speed, the faster you are. Nice. Last question. A study was conducted to investigate the length of the time it took to melt chocolate chips in your mouth. The melt time was measured for 80 students who participated. Here's their 5-number summary. So these are in seconds. Approximately how many chips had a melt time between 12 and 29? Okay, so again, this is a box plot. And so there's the first quarter. This is the lower 25%. So 15, my best number closest to 25 is 20. So I'm going to have to say 20, but wait a minute, that's not in percent. So let's think. It's 25%. What's 25% of 80 people? And of means multiply. So 0.25 times 80 is 20. Oh, even better. Nice work, guys.